Okay, hello and welcome to this talk on our DRAMSec paper Hammulator, where we simulate the Rowhammer effect. And let's first discuss why you should simulate the Rowhammer effect. So for that you have to know that exploits usually need templating of memory, so finding vulnerable memory ranges, and that can take up to hours on some memory models. And even then, exploits are often still unstable, so you have to run them multiple times. Sometimes you get a flip, sometimes you don't. And further, there is no open source possibility yet to test mitigations against such attacks. So the solution for that is to simulate Rowhammer deterministically, so that you always get the same flips and don't need this templating in some cases. And then you could prototype exploits and mitigations rapidly. The problem is that there's no open source Rowhammer simulator yet. And that's what we proposed in our paper. These are the authors, so mainly Lukas and I, both PhD students, did this project together with our supervisor Schwarz. We are all from CISPA. Let's hop right into the background of our paper. So basically we use GEM5. Most of you should know it. It's a modular open source system and processor simulator. So basically what it does, it simulates a whole system for you if you want, with timings or cache timings, etc. And it supports both syscall and full system emulation. Syscall emulation means, okay, you have your kernel and you have your binary, and when the binary runs in GEM5, so on the simulated CPU, and if one does syscalls, basically calls in the original host kernel. And for full system emulation, basically a whole GNU Linux operating system runs in GEM5, but therefore it's kind of slow. And GEM5 also supports some advanced features, that is checkpointing, and we use that in Hammulator to basically go back to some checkpoint in the simulator. You can think of it as just VM snapshotting. That's another term of that. And it supports 2 CPU swapping. And the idea there is you have timing CPUs in GEM5 that are kind of slow because they simulate cache timing and what we do also DRAM timing. And you have fast CPUs, so for example a KVM-based CPU that uses the Linux kernel KVM feature, and that one is really fast. And in our Hammulator we switch between these CPUs. Then there's also DRAMSim 3, which is a cycle-accurate DRAM simulator. It's easily modifiable, and the best part about it is that it can be, or the best part for us is that it can be attached to GEM5 for timing information. So GEM5 simulates the cache timing, and then it goes to DRAMSim 3, and that one does DRAM timing. Okay, now that we have the background for our work, we can already discuss the high-level architecture of Hammulator. And you can see that here on the left side. So basically GEM5 is the base building block of Hammulator. We have DRAMSim 3 here on top. And our Hammulator is outside of this GEM5 structure here, and it gets callbacks and modifies the host memory in GEM5. As I said before, we have multiple CPUs in GEM5. For example, we have this KVM model here that's really fast since it uses the Linux kernel, and we have this timing CPU here, which is kind of slow because it does timing. But both these CPU just access and write the data in GEM5 host memory. And we can swap these two out with this swap CPU function. Just think of it as just a library function where you essentially just call that, and then GEM5 does the CPU switching for you. And now if we use this timing CPU here, you can already see the architecture. We provide timing to DRAMSim 3, which then does the DRAMSim cycle-accurate simulation and callbacks into Hammulator, which then modifies the data here. And the nice part you can already see from this figure is you can just use the timing CPU only for the Rowhammer parts of your exploit. So basically you switch to the timing CPU, you do your hammering. By that, you modify the values here in the host memory, and then you switch back and run in the KVM CPU, but you still see the hammered changes, the flipped bits. Okay, so which effects do we simulate? So basically, Rowhammer is mostly deterministic. What we do, we are basically fully deterministic. You could patch that in some Hammulator extension too. Then, as Kim et al. Report, that for some models, bit flips start at some other threshold than on the other DRAM. We basically support a DRAM-specific hammer count threshold. So you hammer an aggressor row, we count the hammers, and then from some threshold onwards, we flip bits. And then Kim et al. Also report that the log of the hammer count scales linearly with the log of the number of bit flips. For what we do is we do it a little bit simpler. For us, just the hammers count scales linearly with the number of bit flips. You could also extend that. It's just one line change. Then we support up to 5 bit flips in a quad word. For that, you need to know that we decide per quad word if we want to have a bit flip there at the current point. We do that as a performance for performance increase, since it would be hard to decide for each bit for each access to an aggressor row if there should be a bit flip. And then we also support such a blast radius where you can hammer from non-neighbor rows. That is distance greater than 1, and you still flip bits in the victim row. But all this is changeable, parameterizable as you want. Okay, let's discuss the attacks we present in our paper. We have 2 exploits, one full system and one syscall emulation one. And the first one is this Google Project Zero privilege escalation exploit, where the idea is, okay, we spray the memory full with page tables, then we just flip bits randomly in the memory, and the probability that we flip a bit in our own page table is really high, and then with high probability we have access to our own page table, and with some more tricks, we are then basically root on the system. You can imagine that if you have access to your own page table. For that, in Hammulator, no templating is needed. Mind again that could take up to hours on some systems. And in Hammulator, this whole exploit runs in 1 to 2 minutes. And we use 200 megabyte of memory there. That's kind of nice since we don't need to spray that many page tables, and you can't do that on a real system too. And that one runs in full system emulation, of course, since we need access to the page tables directly. And we have 2 other POCs on RSA encryption corruption, where we basically flip bits in the private key, and that one takes 2 minutes and runs in syscall emulation just to show that also works. And syscall emulation is in practice easier to do. Okay, in the following I will play up a video on this page table exploit. I will start it so you can see we boot up Gem 5. Now I mount and run the exploit. The simulator, the exploit first tries to find some bit flips in memory. And as you can see, that goes rather quickly since we are in Hammulator and every row should be flippable. And now the exploit fills the memory with page table entries. It does that here. That takes some time, I would say most of the time of this exploit. You can also see a timer up here. And now you should see that after each stage, the exploit tries to retries if there's still a bit flip at the location it found previously. So for that, we can see it switches here to the timing CPU and then back to the KVM CPU after hammering is done. And now filling up the memory of page tables is finished. The exploit already finished now. But let's quickly discuss what happened here in the last step. So we are running a target executable. For that, you need to know this target executable is a setuid binary, which means, okay, when you run it, we execute as the root user, but we can't change what this binary does. So now we are trying to cause bit flips. We are then searching for a modified page table entry. We find one, and then we basically patch the code of this setuid binary, and then we can basically execute anything as root. And you can see that here with this escape print, which is basically executed as root. Okay, so let's quickly discuss the defenses. We also tried an Hammulator, that is for one probabilistic adjacent row activation proposed by Kim et al. We just tested with the configuration they propose in their work, and for us we did not see any bit flips when we use it. And we implement another panopticon-like countermeasure where we basically count accesses to an aggressor row per victim row, and when this hammer count, we call it, exceeds some threshold, we just refresh the bank, and with that we don't see any bit flips as well. Okay, so let's finish up with some limitations and future work. So as you probably noticed, we don't model any data dependence. DRAMSim 3 does not do that too. You could do that in some extension to Hammulator, and we don't support the effects discovered in half double. So basically, we don't need an access to a near neighbor. Someone could do that too, and that could also be possible with fine-tuned configurations. We see it, and yeah. People could also, that was a topic that came up in the reviews often, people could also further study mitigations in Hammulator, prototype them, test their overhead. Yeah. And with that, I have to already thank you for your attention. And please check out our paper and repository. Here, this QR code leads to the same link here. You can find our project, README, and our paper there. And with that, thank you for your attention again, and I hope for a nice discussion.